going to happen to the acceleration? It changes a function of time. If you want to model it exactly, you've got to include that. Some other subtleties. What's happening on the sides here? Friction forces. We will learn in statics, so we list statics as one of the courses that you're going to do stuff with this, as well as in dynamics, that the friction force is equal to a coefficient times the normal force exerted by the wall on the potato. So if we want to minimize the friction force, we want to have very small amount of force laterally on that thing. But what's the downside? If it's too loose, what happens? You lose the pressure. So there's a fine balance there, yes? In addition, this coefficient will depend critically on whether or not you have a lubricant present. What's a nice lubricant? Any kind of liquid usually, yeah? Don't go there. In fact, engineers are so serious that when we study lubrication, we call it tribology, just so we don't have that kind of thing going on. All right. This then would be lubricant. So what's a good strategy when you shove your potato in? Make the potato, choose a potato that's a little big, put a sharp edge on the top, so that when you shove it in, it cuts the potato. What happens when you cut a potato? Is it moist? Yeah. Have that go down, make sure it doesn't stay in there too long. You'll have a nice lubricant to get that potato going out. Yet you still get a good seal on it, yes? Yeah. Does that make sense to people? All right, let's leave the gun, and let's move on to the potato after it leaves the gun. And let me look at my notes to make sure I didn't forget something. Okay, so now let's suppose that the potato has just left the gun. Kind of like Elvis has left the building, yeah? So we're here, it's out of the gun. Is there anything pushing it anymore? No. So now it's a free projectile in air, yes? You've studied that in physics a bit? Okay, so let's talk a little bit about that. So now we have a projectile. Here's the potato. It's left the gun. Let's suppose that it has an initial velocity. Remember, velocity is a vector, yes? And in fact, let's set it up so that we have x and y, horizontal and vertical. And let's suppose that initially this thing has had some angle, theta. Yeah? The velocity is going to change with time, yes? Why is that? Gravity. We have accelerations, yeah? Unbalanced forces. The unbalanced force is the weight of the object. Is there any force in the x direction? There is, but we tend to ignore it. Okay? Air resistance. Let's talk about it first with no air resistance. This thing is going to go up and over, and eventually it's going to hit the target. We'd like to be able to predict, for a given speed, what angle should we set so we hit the target. That's going to be part of the competition, yeah? Now, let me just preface this by saying that for the potato guns, it's cheap and easy to just keep shooting it and adjusting the angle, yeah? Practice. But what if you were designing the space shuttle, or some kind of ocean-going vessel, or even advanced copiers? Could you build a whole bunch of them and test them to see if how you should adjust the parameters? No, not practical, yes? So that's why we would do analysis on the thing instead. Let's suppose that this thing starts here, we want it to end there. We want to be able to predict path, how far it goes. I'll call that x final, and how this value will know y final, yeah? And actually it's negative, it goes down. Put the origin right there. X and y. Anybody remember our equations? When we do analysis of projectiles, we have to work with x and y separately, yeah? And our equation is the sum of the forces in the x direction, which we said is 0, is mass times the acceleration in the x direction. You guys remember that stuff? If the acceleration is 0, what does that tell us about the velocity in the x direction? Constant. And so we can calculate x final by just doing our constant velocity times time, yeah? Assuming we start from 0. Everybody with me? Now, what's the complication? It's only a minor complication. Do we know the x component? Well, we have to calculate it. So what we're going to do is take our initial velocity times the cosine of the initial angle, yes? Times t. But that's pretty straightforward, yeah? Let's do the y now. In the y direction, and I think you guys have done these, we have the sum of the forces in the y minus mg, yeah? Mass of potato times g is equal to mass times acceleration in the y direction. The masses cancel. Acceleration in the y direction is a constant. It's minus g. If the acceleration is constant, what's our velocity in the y? What is it?
-1/2 gt squared.
Well, that's not the velocity, is it? It's just minus gt, huh? Plus the initial y velocity. Make sense? And then we need to take that one more step. And when we integrate that to get y, because this is dy dt, y as a function of time, or I should say y final. Why don't we just solve for y final? Is equal to the initial y plus the initial velocity times the sine of the initial angle. That's our initial y velocity times time minus a half gt squared, right? That's what somebody remembered. So there's our y. Now, do we know this value when we start out?
Yes.
Yeah, because we have the gun, right? And we know how far it is off the ground or down to the... So we have that. That means in this equation, we can solve for the t. Yes? Assuming we know the initial velocity and the angle. Once we have t, we can go back and get our x final. Because remember, that was b initial cosine theta I times t. Yes? Anybody with me? So we can actually predict where this is going to hit just from this set of equations, assuming you know this initial angle, which you should be able to get. The initial velocity is a little harder. Yep? A little harder. Okay, so we're going to learn all that stuff and do it again. You did it in physics once, probably. Yeah? You'll do it again in dynamics. So we're going to have lots of fun. We'll do a lot of projectiles. Okay, but then they're going to add a wrinkle, because is this realistic, especially if you're going very fast and over long distances? So now you're shooting a ballistic missile someplace. Well, let's do a peaceful, I don't know, what's peaceful? That you can shoot long distance at high speed. I don't know what. Think of something.
A life jacket. A t-shirt at a concert.
T-shirt at a concert, that would be an example, because that has a lot of air resistance. But the key is we want to add in resistance of the air. Resistance of the air. Alrighty? That's where the aerodynamics and fluid mechanics and transport phenomena are going to come in. And in fact, we're going to erase all of this. Let me list you a couple more classes that are going to be involved. Fluid mechanics, you guys will take next year. Transport phenomena, you will take the year after. If you're in the aerospace option, we'll take aerodynamics. And if you're in the graduate program of BSMS, you'll take something called ideal flows. And perhaps some other ones